In this video, we're going to be discussing measures of center. So we're looking at ways of determining where the center or the middle of a distribution lies. So we're going to start off here with the three types of, or three common measures of center. The first one is the mean, which we also refer to as the average. And I'm going to put a star by that one. That's the one we're going to use throughout most of the course. We're going to also look at the median, and then finally briefly look at the mode. Okay, so the mean or the average is going to be denoted with this X bar notation when we are finding the mean for a sample of data. Okay. Versus a population, right? So when I'm saying the mean for a sample, specifically what I'm referring to is that we are not calculating the mean for the whole population. We're just calculating it for a sample, a subset from the population. And when we do that, the notation is X bar. If we were to calculate the mean for the entire population, which we'll do a little bit later, that notation is the Greek letter mu, so it looks kind of like a U there with a curly tail on each end. Okay, so we'll come back to that. In either case, the way that you calculate the mean is you add up all the observations. So this is the Greek letter capital sigma, and in mathematics it just means the sum of. So we're going to take the sum of all of our observed values of x and then divide by how many of them there are. So we're going to go ahead and go straight to an example where we're given a data set on the exam scores for 15 students in a college math course. And what we're asked to do is find the mean exam score. So we're going to use the X bar notation to show this is the mean for this sample of 15 students. We would add up all of these observed values. And I'm going to use kind of a shorthand notation. So we're adding up all 15 values and then dividing by 15. So we need to take the sum of those data values. So we have 72 plus 82 plus 78 plus 90 plus 75 plus 72, plus 68, plus 87, plus 70, plus 74, plus 65, plus 19. We should pay attention to the fact that that one's unusual. Plus 72, plus 74, and plus 96. So that gives us a sum there of 1,094 as our numerator. Our denominator is 15. And so when we take that 1,094 and divide by 15, we get 72.93 if we round. Okay. Next thing that we're asked to do here is recalculate this mean exam score, excluding the 19. And that 19, we're going to come back and talk about what we think that is. That is called a potential outlier. It looks unusual when compared with the rest of the exam scores. I am not trying to tell you that you should just throw out values that look unusual. What I am trying to show you is what would happen if this data set had not contained that value of 19. And in that case, there would have been only 14 data values, and that numerator, instead of being 1,094, if the 19 was not part of that sum, it would have been 1,075, which would have resulted in a sample mean of 76.79. Okay, so what I am trying to demonstrate there is that you'll notice that mean, that sample mean, increased fairly significantly, right? Just by excluding that one really low value of 19. And that is an indicator to us that the mean as a measure of center is not resistant, meaning that it is influenced by these extreme observations. So I'm just going to jot a note here that says the mean is not a resistant measure of center. Okay. You can see that especially here because we had a fairly small data set of only 15 students. So if one of those scores is very low, it is going to significantly pull that mean down, which is what we saw happen. If we had a much larger data set, so maybe we had 100 students and we only had one student that scored way down low at 19, then that potential outlier wouldn't nearly as dramatically affect the sample mean as it did in our case with a small sample size. At the bottom of the page, just as a quick summary of what I already gave you, which is the change in symbol that we use if we're looking at taking the mean for an entire population instead of a sample. The process is the same. Add up all the values and divide by how many there were. You'll notice we use capital N this time because capital N is population size, whereas lowercase n was sample size. And then we're using this Greek letter mu instead of x bar. So continuing on here, we're now at our second measure of center. This one is the median. And so the median is the value in the middle of a data set such that exactly half of all observations are less than the median and half of all observations are greater than the median. So the notation that we're going to use here is a capital M that represents our sample median. I've got a process here for us to use, but I just want to remind you one more thing. So when we're calculating the median, we're looking at the value directly in the middle of the data set. So half the values are smaller and half the values are larger. It's kind of like the median on the road, right? The median is sometimes that concrete barrier that divides one half of the road from the other half. And so same idea here. So our process in finding the median is we're going to order our list from smallest to largest and then find the position of our median using the formula n plus 1 over 2. So we're going to go back to that exam score data set, and the first thing that we need to do then in step 1 is order the data from smallest to largest. So I'm going to try and see if we can have that data, there we go, that data in view. So smallest was definitely the 19. And then from there, we had a 68, I'm looking for values in the 60s, and a 65. So we have 65, 68. And then we'll go into the 70s. Looks like we have a 70, and then we have 3 72s. And then 2 74s, followed by a 75 and a 78. And then in the 80s, we've got an 82, an 87. And then in the 90s, we've got a 90 and a 96. Okay, so also as a reminder, we were supposed to have 15 values there. And so we do have 15. That's a good double check just to make sure we didn't leave any out. Step 2, we're going to find the position of the median using the formula n plus 1 over 2. So n plus 1 over 2 does not find the value of the median. It finds the position of the median in your ordered list. In other words, here's the first position, the second position, the third position, etc. So n is our sample size, that was 15. 15 plus 1 over 2 is 16 over 2, which is 8. That doesn't mean the median is 8. That wouldn't even make sense, right? 8 does not look like the middle value in this list. The middle value looks somewhere in here, and it's telling me this is the 8th position. So 1, 2, 3, 4, 5, 6, 7, 8 is right there. And so we would say that our median is 74. Okay, we're going to do this same process again. This time, just like we did with the mean, we're going to leave out that really low exam score of 19. And so if we order the list again, we already have it from above. We would just be leaving out the 19 at the beginning. And for step 2, we now only have 14 values in the list. And when you have an even number of observations, an even number plus 1 is going to give you an odd number, which means your division by 2 is going to always give you a half there. So this is telling you that we need to look in the 7.5 position. When that happens, you're just going to take the average or the mean of the 7th and 8th. So 1, 2, 3, 4, 5, 6, 7, and 8. So I've got those two values. So in this case, since they're the same, I would just take 74. If they were different, just so you know what we would do, we would add those two values together, divide by 2, and whatever we got would be our median. So you'll notice here that whereas that mean changed fairly significantly with dropping the 19, the median in this case didn't change at all. Sometimes it will change, but usually not dramatically. So I just wanted you to notice that the median is resistant, whereas we said the mean was not, right? The median is resistant, meaning it is not highly influenced by those potential outliers. Okay. Lastly here, in terms of our measure of center, the last one that we look at is the mode. By definition, this is the most frequently occurring value in the data set. And really the only reason that we look at the mode at all is that it is the one that's useful for measuring center when you have qualitative data. Remember, this is non-numeric. So if I have non-numeric data, like maybe I'm looking at eye color, I can't find the mean eye color, right? I can't add them all up. I can't find the median eye color because I can't order eye color from smallest to largest. And so in those types of qualitative data cases, we need a different way of measuring center, and that is mode. So just a few examples here. A data set can have no mode if all observations occur exactly once. So if my data set consists of red, yellow, white, green, blue, and pink, each one of those data values occurs one time, we would say there's no mode. Another example, a data set can have multiple modes if multiple observations are the most frequently occurring. So if I have a data set red, yellow, white, white, red, pink, white occurs twice, and then red also occurs twice. And so we would say there are two modes. And by the way, the two modes are because we have two colors that both occur most frequently, red and white. It is not because they each happen to occur twice, okay? And then lastly here, a data set can have a mode of 0 if 0 is the most frequently occurring value. So in this data set, right, 0, 0, 0, 3, 3, 10, 13, and 19, the mode is 0, which means 0 is the value that occurs most frequently, okay? So I just wanted to make sure we understood that a mode of 0 versus no mode, those are different things.